Good day, class. This time, today we begin one of our most important technical foundation in tropical design, environmental and climatic analysis. On our previous lessons, we discussed how climate influences architecture conceptually and historically. Now, we move into scientific environmental analysis. This topic is critical because climate responsive architecture cannot rely on assumptions alone. Architects must understand how to collect, interpret, and apply climatic data in order to make intelligent design decisions. The topics we will study includes sun path analysis, wind rose interpretation, psychometric charts, thermal comfort indices, environmental data interpretation, and building orientation analysis. These analytical tools helps architects understand how environmental forces behave across a site and how buildings interact with climate. In tropical architecture, environmental analysis influences the following: building orientation, window placement, ventilation strategies, solar protection, daylighting, thermal comfort, and energy efficiency. Environmental analysis transforms architecture from purely artistic composition into evidence based environmental problem solving. This lesson, therefore, represents a major transition from conceptual understanding towards technical environmental design intelligence. One of the biggest mistakes in architecture is designing buildings without understanding environmental behavior. Environmental analysis is important because buildings continually interact with climate. Every building responds to the following: sunlight, wind, heat, rainfall, humidity, and temperature changes. If architects fail to analyze these environmental conditions, buildings often become overheated, poorly ventilated, energy inefficient, uncomfortable, and environmentally unsustainable. Environmental analysis allows architects to predict environmental behavior before construction begins. For example, where will sunlight strike the building? Which directions receive the strongest winds? Which areas experience excessive heat gain? Which orientation improves airflow? And which spaces receive optimal daylight? Answering these questions allows architects to design more intelligently. Environmental analysis, therefore, improves thermal comfort, sustainability, building in efficiency, human well being, and environmental performance. In tropical architecture, this process becomes especially important because climatic conditions are intense and highly influential. Environmental analysis begins with understanding climatic data. Climatic data refers to measurable environmental information used to analyze site conditions and environmental behavior. Several major environmental variables influence architecture. The first is temperature, which affects thermal comfort and heat gain. The second is humidity. In tropical climates, humidity strongly influences occupant comfort because it affects the body's ability to cool itself. Solar radiation is another major factor because sunlight transfers heat into buildings through roofs, walls, and glass surfaces. Wind speed and wind direction influences ventilation, airflow, cooling potential, and rain penetration. While rainfall affects drainage design, roof systems, moisture protection, and flood management. Architects collect and analyze this environmental data to develop climate responsive strategies. Environmental analysis transforms architecture into a specific and evidence based discipline. Tropical regions do not all behave identically environmentally. There are several tropical climate types, each requiring different architectural responses. The first and most common in the Philippines is the hot, humid climate characterized by high temperatures, high humidity, heavy rainfall, and stronger solar exposure. Hot, humid climates requires maximum ventilation, moisture control, solar protection, and lightweight materials. Hot, dry climates, on the other hand, prioritizes thermal mass, heat buffering, limited solar exposure, and night cooling. Monsoon tropical climates experience strong seasonal rainfall and changing wind patterns. Tropical rainforest climates experience continuous rainfall, dense humidity, and minimal seasonal variation. Each climate type influences building form, materials, ventilation systems, roof configurations, and spatial organization. This demonstrates that climate responsive architecture must always adapt specifically to local environmental conditions. One of the most important environmental analysis tools in architecture is sun path analysis. Sun path analysis studies how the sun moves across the sky during different times of the day and different seasons of the year. This is extremely important because sunlight directly affects heat gain, daylighting, thermal comfort, and energy performance. Architects use sun path analysis to determine which building surfaces receives the most sunlight. When sunlight enters spaces, how shadows behave, and where shading systems are needed. In tropical climates, solar control becomes extremely important because excessive sunlight increases indoor heat significantly. For example, Western sunlight often creates severe afternoon heat gain. Therefore, architects may reduce western openings or add shading systems. Sun path analysis also improves daylighting strategies by allowing architects to maximize natural light while minimizing heat gain. This tool therefore directly influences building orientation, facade design, window placement, roof overhangs, and shading systems. Environmental analysis allows architects to predict solar behavior before construction begins. After understanding sun path analysis, we must now understand solar radiation and heat gain. Solar radiation refers to the energy emitted by the sun that reaches building surfaces. In tropical climates, solar radiation is extremely intense and significantly affects building performance. There are several forms of heat gain. First is direct solar radiation, where sunlight directly strikes building surfaces. Second is reflected heat, where nearby surfaces such as pavements or neighboring buildings reflect solar energy toward structures. Third is conducted heat, where heat transfer through materials such as roofs and walls. These heat transfers strongly influence indoor thermal comfort. Among all building elements, roofs usually receive the highest amount of solar exposure in tropical climates. This is why roof design becomes extremely important. Glass surfaces are also major contributors to heat gain because sunlight easily penetrates transparent materials. Architects, therefore, analyze solar intensity, surface exposure, material behavior, and shading requirements to minimize overheating. Understanding solar heat gain allows architects to develop effective passive cooling strategies. Shadow analysis is closely related to sun path analysis. Architects use shadow studies to understand how shadows move across buildings and sites throughout the day. This analysis helps determine which areas receive excessive sunlight, which spaces remain shaded, and how neighboring structures affects solar exposure. Shading is extremely important in tropical architecture because excessive heat gain causes thermal discomfort and increases cooling demand. Architects therefore design shading systems to protect buildings from direct sunlight. Examples include roof overhangs, louvers, brise soleil, vertical fins, and vegetations. Proper shading significantly improves indoor comfort, energy efficiency, daylighting quality, and environmental performance. Good tropical architecture balances sunlight and shade carefully. The goal is not to eliminate sunlight completely, but rather to control it intelligently. Wind is another major environmental factors in tropical design. Air movement significantly affects thermal comfort, especially in hot, humid climates. Wind analysis helps architects understand wind direction, wind speed, seasonal airflow patterns, and ventilation potential. Good ventilation improves comfort by removing heat, reducing humidity, enhancing air quality, and cooling occupants. Architects therefore study how wind behaves across sites and around buildings. Wind also affects moisture movement, rain penetration, outdoor comfort, and environmental cooling. Understanding wind behavior allows architects to optimize window placement, building orientation, spatial organization, and ventilation systems. Traditional tropical architecture demonstrates excellent responses to prevailing wind conditions. One of the most important tools used in environmental analysis is the wind rose diagram. A wind rose graphically represents wind direction, wind frequency, wind intensity, and seasonal airflow behavior. Architects use wind roses to identify prevailing wind directions and optimize natural ventilation strategies. For example, if prevailing winds come from the northeast, architects may position openings to capture airflow more effectively. Windrow's interpretation influences building orientation, window placement, courtyard positioning, ventilation pathways, and outdoor space design. Understanding prevailing wind behavior is especially important in tropical climates because airflow significantly improves comfort. Wind analysis, therefore, becomes a critical component of climate responsive architecture. One major application of wind analysis is cross ventilation design. Cross ventilation occurs when air flows naturally through spaces from one opening to another. For cross ventilation to function effectively, buildings require properly positioned openings, minimal airflow obstruction, alignment with prevailing winds, and continuous airflow paths. Cross ventilation significantly improves thermal comfort, air quality, heat removal, and passive cooling performance. Traditional tropical architecture often demonstrates highly effective cross ventilation systems. Open floor plans, large windows, elevated structures, and permeable walls. Architects analyze airflow behavior carefully to optimize ventilation performance. This demonstrates how environmental analysis directly influences spatial planning and building form. Another important ventilation strategy analyzed in tropical architecture is the stack effect. The stack effect occurs because warm air naturally rises. Architects use this environmental principle to create vertical airflow systems that remove hot air from buildings. When warm air rises and exits through upper openings, cooler air enters lower openings, creating continuous airflow movement. Stock ventilation is commonly integrated through atriums, clerestory windows, roof vents, double height spaces, and ventilation towers. This passive strategy improves heat dissipation, thermal comfort, and indoor air movement. Stock effect analysis helps architects understand how building height, openings, and vertical spaces influence airflow behavior. This demonstrates how architecture can work with natural environmental physics rather than depending entirely on mechanical systems. One of the most advanced environmental tools used in climate responsive architecture is the psychometric chart. A psychometric chart graphically represents the relationship between temperature, humidity, air conditions, and human comfort. Architects use psychometric charts to analyze environmental conditions and determine which passive strategies can improve comfort. The chart helps identify comfort zones, ventilation requirements, cooling opportunities, and moisture conditions. For example, a psychometric chart may indicate whether natural ventilation alone can achieve comfort or whether additional cooling strategies are necessary. This tool transforms climatic data into practical architectural design decisions. Psychometric analysis is widely used in sustainable architecture, environmental simulations, building performance studies, and climate responsive designs. Understanding psychometric charts helps architects make scientifically informed environmental decisions. One of the most important goals of tropical architecture is achieving thermal comfort. Thermal comfort refers to the condition where occupants feel physically comfortable within a space. However, comfort is not determined solely by temperature. Several environmental and physiological factors influence human comfort, including air temperature, humidity, air velocity, surface temperatures, human clothing, and physical activity levels. Architects therefore use thermal comfort indices to evaluate environmental suitability. One commonly used model is PMV, or Predicted Mean Vote, which predicts how occupants may perceive environmental conditions. Another approach is the adaptive comfort model, which recognizes that humans psychologically adapt to their environmental conditions over time. Thermal comfort analysis helps architects determine whether spaces require more ventilation, better shading, cooling strategies, material adjustments, and environmental modifications. In tropical climates, thermal comfort analysis becomes especially important because environmental conditions are often extreme. The purpose of climatic responsive architecture is ultimately improve human comfort while minimizing energy consumption. Collecting environmental data alone is not enough. Architects must also learn how to interpret environmental information correctly. Environmental data interpretation involves transforming climatic information into practical architectural decisions. Architects analyze historical weather records, temperature fluctuations, humidity levels, wind patterns, solar exposure, and rainfall intensity. This information helps determine appropriate orientation, ventilation requirements, material suitability, roof design, shading strategies, and site planning approaches. For example, if a site experiences strong western solar exposure, architects may reduce western glazing or introduce shading devices. Similarly, if prevailing winds come from a particular direction, buildings may be oriented to maximize natural ventilation. Environmental interpretation allows architects to predict environmental behavior before construction occurs. This demonstrates that climate responsive architecture depends heavily on scientific analysis and environmental reasoning. Building orientation is one of the most critical environmental decisions in architecture. Orientation determines how buildings interact with sunlight, wind, environmental conditions. Good orientation improves thermal comfort, ventilation, daylighting, and energy efficiency. Poor orientation creates excessive heat gain, glare, poor airflow, and increased cooling loads. In tropical climates, minimizing Western solar exposure becomes extremely important because afternoon sunlight produces severe heat accumulation. Architects, therefore, study solar movement and wind behavior carefully before determining building orientation. Orientation analysis also affects window placement, shading systems, interior planning, outdoor comfort, and building massing. This demonstrates that climate responsive design begins at the earliest planning stages. Beyond regional climate, architects must also understand microclimate conditions. Microclimate refers to localized environmental conditions within a specific site. Several factors influence site microclimate, including vegetation, topography, water bodies, adjacent buildings, and surface materials. For example, areas with dense vegetation are often cooler because plants provide shade and reduce heat buildup. Water bodies can influence humidity and cooling effects. Urban areas with excessive concrete often experience higher temperature because hard surfaces absorb and radiate heat. Microclimate analysis helps architects determine comfortable outdoor areas, optimal building placement, ventilation pathways, and solar exposure conditions. This analysis allows architects to manipulate environmental conditions strategically through site planning and landscape integration. Daylighting analysis studies how natural light enters buildings and affects interior spaces. Natural light significantly improves visual comfort, psychological well being, spatial quality, and energy efficiency. So architects therefore analyze window placement, sun angles, interior reflectivity, shading systems, and light penetration. Good day lighting reduces dependence on artificial lighting during daytime. However, uncontrolled daylight may also create excessive glare, heat gain, and visual discomfort. Therefore, tropical architecture carefully balances light admission, solar protection, and thermal comfort. Environmental analysis allows architects to optimize daylight quality while minimizing environmental problems. Tropical climate experience intense rainfall, which creates significant architectural challenges. Architects must therefore analyze rainfall behavior carefully. Heavy rainfall affects roof performance, drainage systems, material durability, flood risks, and moisture control. Poor water management may lead to structural damage, interior leakage, mold growth, and flooding. Traditional tropical architecture often addressed rainfall through steep roofs, elevated flooring, wide overhangs, and permeable landscapes. Modern climate responsive architecture continues using similar principles while integrating contemporary technologies. Water sensitive design is becoming increasingly important because climate change intensifies flooding risks in many tropical cities. Today, architects increasingly use digital simulation tools to analyze environmental performance. Environmental simulation software allows architects to predict building behavior before construction. Common tools include SunPath software, airflow simulations, energy modeling programs, daylight analysis software, and BIM environmental systems. These technologies helps architects optimize building performance, reduce energy use, improve comfort, and test environmental strategies. Simulation tools support evidence based design and improve environmental decision making. However, technology should support architectural thinking, not replace it. Architects must still understand environmental principles fundamentally. Environmental analysis should not be treated as a separate technical exercise disconnected from design. Instead, environmental understanding should guide the architectural process from the beginning. Environmental analysis influences conceptual design, site planning, building orientation, material selection, spatial organization, and sustainability strategies. Good architecture emerges from understanding environmental conditions deeply. Climate responsive design is therefore both analytical and creative. Environmental intelligence becomes part of architectural thinking itself. Let us examine how environmental analysis translates into real architecture. This case study demonstrates a building designed according to climatic conditions. Notice how environmental analysis influences orientation, window placement, roof design, shading systems, and ventilation pathways. The building minimizes heat gain while maximizing airflow and natural light. This demonstrates how environmental analysis directly improves architectural performance. Many buildings fail environmentally because architects ignore climatic analysis. Common mistakes include poor orientation, excessive glazing, minimal ventilation, inadequate shading, and lack of environmental understanding. These problems increase heat gain, energy use, thermal discomfort, and operational costs. Environmental analysis helps architects avoid these failures by informing intelligent design decisions. Today, we learned that climate responsive architecture depends heavily on environmental analysis. Architects must understand solar behavior, wind movement, thermal comfort, environmental data, and site conditions. Environmental analysis transforms architecture into evidence based environmental design. Good. Tropical architecture responds intelligently to climate rather than ignoring environmental realities. So, as future architects, it is important to recognize that environmental analysis is not optional. Architecture affects energy use, comfort, sustainability, and environmental quality. Reflect on how architectural or rather environmental understanding can improve architecture and how poor environmental decision negatively affects both buildings and communities. On our next lesson, we will apply environmental analysis directly into passive environmental systems. We will study how architecture itself can improve comfort naturally through ventilation, shading, passive cooling, and daylighting. This systems represents that practical application of the environmental analysis tools we studied today. This concludes our discussions for week 3 and 4 on environmental and climatic analysis.